The broadcast is now starting. All attendees are in listen-only mode.
Hi everyone, thanks for joining our fourth session of the Cambium College program. Today we're going to be talking about transmission schemes and frequency bands, and our presenter is Dave Geithner. He's a really great guy. He's part of our systems architecture team, so he knows a lot about wireless and creating wireless networks. As always, be sure to type any questions you have as you think of them into the text box on the right, and we'll get to them throughout the presentation. So without further ado, here's Dave.
All right, so thanks, Colin. I appreciate it. I also appreciate the really great guy comment. We'll see how that holds as we continue through here. So again, welcome to the next session of the Cambium College. My name's David Geithner, so we'll move along here. Let me kind of build this out here. So the Cambium College is basically before we kind of get into where we're going with tonight's session, perhaps we can spend maybe just a few seconds talking about where we've been and where we're at in the overall series here. The Cambium College series for this year is broken up into a three-series approach. First being a foundational level series where we've been giving you a lot of background on just general radio topics, things that relate to propagation, interference, as you can kind of see here, different types of radio types, what have you. Tonight's session, transmission schemes and frequency bands, perhaps not necessarily in that order. We may flip-flop it around a little bit as we walk through here, but that's generally the theme. We'll wrap that up, or this series up, this overall foundational series up next 2 weeks, I believe. We're trying to do an every 2-week type of cadence. And then we'll move into applications where we start talking about how are these radio technologies applied to different applications, and we'll get into there, and then wrapping it up later in the year with optimization. All right, so that's kind of where we've been, what we're going to be doing tonight. One other quick note about this slide: neither of those two gentlemen that are in that picture are me. And I'm not really a hat person, and B, there's nowhere in Illinois you're going to see mountains in the background like that. So it's definitely not me. Anyway, so moving on here. We'll get right into the topic, RF spectrum and frequency bands. So here's some questions that many of you may be asking. What exactly is wireless spectrum or RF spectrum, and why does it really matter? Whenever we're communicating wirelessly in any manner, we need to be using some portion of what's called RF spectrum. And so as you kind of look at the pictures that are on this slide here, the garage door remote opener, that's a wireless frequency that's going from the remote to the control unit inside the garage that's opening and closing the door. That's not just a randomly selected arbitrary frequency that just somebody pulled out who was designing that thing to make that door open. That was actually an allocated, so to speak, frequency for that type of a purpose. We'll talk a little bit about that as we continue on. Same thing goes with some of these other slides, or these other pictures that you see here. The fireman that's talking on the radio that has in his hand there. Certainly, as he's communicating critical type of information about the job he's doing, he's not wanting to hear all of a sudden a baby monitor pop up onto that walkie-talkie and hear a baby crying or something of that nature. That frequency is very, very controlled that he's using on that radio. And then, of course, well, maybe not necessarily of course, but cellular networks. So as you're using your cell phone, your smartphone, whether you're dealing with Verizon, the big type players, Verizon or AT&T or T-Mobile or what have you, the frequencies that your cell phones are using are allocated, they're controlled, and again, we'll talk a little bit more about how that's done. So point being here is that whenever we're communicating wirelessly in any manner, simple things like remotes or critical things like fire, police, defense, things like that, or just your common cell phone, we're using a portion of RF spectrum to do this. All right, so we'll move on a little bit here. These These are certainly good questions about what is the wireless spectrum. Good place to start. Maybe we might want to step back a little bit and understand this a little bit more. Some of the Cambium College webinars that were been presented in the past that basically is telling you that all wireless communication signals travel through the air via radio frequencies, aka spectrum. So TV broadcasts that you watch at home, and not the cable TV, but TV over the air. If you have rabbit ears or some kind of an antenna on your house that you're capturing the TV signal from the air, that's RF spectrum. Radio program you listen to in the car. GPS navigation device that your car has that helps you get to where you're going. And of course, as we've talked about, the wireless cell phone services that you use to make calls and check Facebook from your smartphone. All of these things are using invisible airwaves to transmit bits of information through the air. So drilling down a little bit on one of those examples again, probably the easiest one is that car radio as you're driving in the car and you select a particular station, just make up a number here, 93.9 FM or something, and you're tuned into a specific station that is broadcasting on that specific frequencies, and you're listening to whatever it is, whether it's jazz or country or talk radio or whatever it is. Or if you have a 15-year-old daughter like I do who just recently saw and now loves Alexander Hamilton musical songs, then you're listening to something Alexander Hamilton. Until you decide you're bored with that channel, and then you press the seek button. Back in the day, you used to turn a dial, but today now it's all pressing seek and seek buttons, and you move to another frequency, 104.7 or something like that. So it's a different radio station transmitting at a different particular frequency, so you hear the new music or the new talk or what have you. The point being with all this is that no two stations transmit over the same spectrum at the same time in the same area, because if they did, they would cause interference. And Seth talked a lot about interference and mitigation techniques with interference. So interference typically is not something that you want, and so you need to control who's talking on what channels, on what frequencies, in order to avoid these common interference elements. Also, because wireless signals can't transmit over certain long distances, you won't be able to tune in a radio station that broadcasts, say, out of New York City when you're in Philadelphia or when you're in Chicago or anywhere beyond the distance that those broadcast signals can travel via the spectrum over the air that your radio is listening to. So anyways, let's get a more grounded here and kind of look at this RF spectrum concept, give it a little bit more context by using some of these charts here. And yes, these charts are freely available on the internet. That's where most of them were originated. Hopefully they'll explain a few things to us about RF spectrum. So when you think of light, like most of us probably think of just what your eyes can see, but the light which our eyes can see or our eyes are sensitive to is only really just the beginning. It's just a sliver of the total amount of light that surrounds us. You'll see here this chart says electromagnetic spectrum. This is the term used by people in the kind of in the scientific or wireless business to describe the entire range of light that exists, that electromagnetic spectrum. So here's what may be the big news for many of you. Light doesn't simply just stop at red or violet like what you see. I don't know if you can see my mouse moving here. Okay, Colin, can you see my mouse moving by chance? Or
yeah, I can.
Let me see if I can grab one of these drawing menu thingies here. Give control of people or mouse, drawing tools, highlighter. How about that? So in this area here, can you see that?
Yep.
All right. So when the light that our eyes are able to see isn't just where you know this whole thing stops. This electromagnetic spectrum stops. Really, it's just a kind of like I said, a real small sliver that it's just what our eyes can see. So radio waves basically kind of go, or this whole electromagnetic spectrum kind of goes from what we kind of term radio frequency areas or waves all the way up to ultra or gamma rays and X-rays and things like that. You can see kind of from these pictures that are kind of placed along the line as well, perhaps some of the types of things where these lower frequencies are used, and kind of the area where we'll be talking about most of the time tonight. So radio towers, TV, FM radio towers, mobile phones and towers like that, and then visible light, and then areas where it starts to get a little dangerous, you know, medical X-rays and radioactivity up in that area. So with regards to radio waves and microwaves specifically, which as seen on this chart as being the longest wavelengths and the lowest energies of light, these are used for many different use cases: scientific, exploratory, medical, communications-oriented use cases. For purposes of tonight's discussion, we'll focus on the communication use cases for these. All wireless technology use airwaves to transmit and receive information. And in order to create an environment where many different technologies can use the airwaves simultaneously, the wireless spectrum is carved into chunks called frequency bands. So for example, as we talked about a little bit earlier, we have broadcast television, assigned to VHF band, AM bands for radio, so on and so on and so on and so on. Who coordinates all this stuff? Federal Communications Commission, which also known as the FCC in the United States anyways, is the government agency that keeps track of who's using which sliver of spectrum. So who's, from a radio perspective, who's using a sliver of spectrum in this area here. This agency grants companies licenses to use the spectrum, but not all spectrum is licensed. There's unlicensed as well. We'll talk a little bit about that in a future slide here. So all of this coordination of various different radio frequencies is probably a very simple task, you would think, right? Well, let's take a look. Let's move on here. I can get this guy. There we go. Oh, why it took so long. I hope it's not going to be delayed and all of a sudden fast forward a bunch of slides. But anyway, so, you know, obviously, holy cow, Batman, as far as all this different spectrum that's available. So this is just that one sliver kind of drilled down, but that one sliver in the electromagnetic spectrum drilled down in the radio portion of it. And literally hundreds, if not thousands of different radio spectrum allocations for different uses are being managed here. We're certainly not going to go through all the details of all these in this particular webinar, but take a look at the high level, some of the high level service groupings that are shown on the chart here, just kind of get you somewhat grounded with all the different entities that would be allocated and controlled and managed through allocations that the FCC tries to manage here. You have aeronautical, you have you know, amateur satellite, you got broadcast satellite, some fixed, land mobile, satellite, land mobile, so on and so on and so on, space research. You have down here at the bottom government exclusive, government agencies. Those are very controlled frequencies, as you can imagine. But creating a chart like this, creating an allocation map like this, and then defining rules around it is how, or at least the first portion of how we ensure that when the fireman comes to your house and tries to talk on the radio to tell his counterparts to go around the back and hit the fire from one angle or another, he's not going to all of a sudden hear a baby monitor pop up on his walkie-talkie or to be able to now start interfering with what he's communicating with. It's all controlled. It's all controlled by a huge chart allocation like this to help manage who's has what portions of spectrum to be able to use their particular devices on for certain different purposes. That's a brief little summary on a very, very complicated allocation process, but I think you get the picture. I think you get the idea. So let's just talk about a few key valuation points on some of these things. First off, talking about frequency, well, basically lower frequencies versus higher frequencies, and are there any real differences or values or attributes about those that we should maybe understand a little bit. So lower frequencies in that allocation map, and when I say lower frequencies, I'm talking about generally, you know, it's kind of rough, but generally less than a gigahertz, so a gigahertz down. They often, or they do, travel farther distances with less energy. They have a ability to deal with obstacles that are in their way a lot better than higher frequencies. So obstacles like trees or buildings or just generally things, billboards, what have you, have a relatively small effect on attenuating this low frequency RF energy. So that's very valuable when you're dealing with you know, trying to get very mission critical type information from one place to another. One of the hindrances is that there's a relatively limited amount of spectrum in this lower frequency range. So if you have a lot of critical information, infrastructure, and again, like we were talking earlier, perhaps police, fire, what have you, wanting to all utilize this very valuable frequency because of some of these key valuation points, then you have some challenges ahead of you. With higher frequencies, greater than a gigahertz, perhaps takes a bit more energy to travel farther distances. Obstacles are a little bit more challenging for them to have to deal with. But on the plus side, there's a lot more available spectrum available to be utilized in this area. So if you have technologies that are able to take advantage and deal with some of the things that we're talking about here in the bullet points above, it's a great frequency to use, or it's a great space to work in as well. So both have some pros and some cons, and technologies have been developed around these pros and cons to leverage and utilize them in the best way they can in the places where they need to be used. What else about radio spectrum? So another attribute that we should probably talk about, and I think I alluded to in some of the earlier slides, is that there's this concept of licensed spectrum and unlicensed spectrum. So with licensed spectrum, applications that typically requires an application for its usage, or application for usage is required. Applying for this application can take some time, so it's something that you got to plan ahead for if you're going to want to try to use some type of a licensed spectrum for some type of an application, because you got to go through some processes, and it's not just to go to this, you know, go online, fill something out, and immediately you have it. It also usually requires a bit of a fee. Now, sometimes it's a small fee, sometimes it's an enormous fee. So, for instance, the AT&T or Verizon spectrum that's used for your cell phones are billions and billions of dollars paid for that spectrum in order to serve the millions and millions of customers that these service providers service across the nation. So it can be substantial. Not all spectrum is that kind of dollars, but I'm just kind of giving you a relative feel. When you're utilizing licensed spectrum, the whole point is to try to provide some amount of protection for the user from any type of interference, meaning somebody else using that same spectrum or that same sliver of frequency for a different type of use case than what you're trying to use it for. So that's the key thing about licensed spectrum, provide some amount of protection. On the converse, there is certainly quite a bit of unlicensed spectrum around that can be used without any type of application or fee paid, and one of the real beauties about that is it's immediate. If you feel you want to use some unlicensed spectrum for some type of a use case, you can do it today, you can do it tomorrow, you can do it this minute, you can do it next week, you can do it without having to go through any application or fee or any type of coordination of that. Very, very attractive for those type of really quick use cases. With new additional allocations, typically it's available for use straight away. And there's no legal, well, the downside, or perhaps one of the downsides, is there's no legal protection for the user from any interference. So if you're doing something in an outdoor scenario and your neighbor's doing something on that same frequency, you have to coordinate on your own. You have to negotiate some things or things like that. There's no real, you don't have any exclusivity of that particular spectrum. All right. So that's certainly something we need to make sure that we understand about some of the spectrum, radio spectrum attributes. Some examples of uses with the bands. I'm not going to, there's a couple of slides here of this, but I'm not going to go through necessarily all of them. But I just want to kind of give you a feel. Also kind of denote for these different types of use cases, are these licensed or unlicensed? Let's touch on maybe just a few of these here. So these real low spectrum bands, so like I mentioned before, a gig or below. So you see all these are kind of certainly below a gig, so they're often viewed as somewhat valued because of their propagation attributes. VHF, original standard for push-to-talk, used a lot in maritime, so ships, boats, people that are out in the ocean definitely want to make sure they're staying in communication with the shore or Coast Guard or what have you for obvious reasons. Don't want to get lost at sea or something like that. They need to make sure they have a very, very good piece of spectrum to be able to use that has great propagation attributes, and it's not going to be challenged with any type of long distance or problems that you might arise at sea. What else? UHF, certainly used for SCADA type of applications. So SCADA being things like controlling maybe some of the utility applications that are out there. You'll see maybe some smart meters that are utilizing this this particular frequency band. You also see that a lot maybe in 900 megahertz as well. Licensed spectrum as well, so protection when your utilities are using these type of spectrums, or well, I guess we'll just kind of leave it at that. 700 megahertz. This is a new spectrum for public safety that was over the last few years recently allocated. So this one is specifically reserved only for public safety type of usage. 800 megahertz. You can see here utilized for some public safety as well as other push-to-talk type services. You'll see 800 megahertz sometimes in taxi cabs or sometimes in construction, things like that. 900 megahertz is actually a unlicensed portion of this very valued space, so obviously you'll see it being more often than not somewhat congested, as it refers to here, a sometimes very overused license-free spectrum because of its high value with being a low frequency, goes far, is able to go around objects through trees, things like that. You'll see it used all over the place. Again, so I'm not going to go through every single one here, like we talked about 2.4 on the prior slide, but you can get a feel, again, for all these different slivers of spectrum, how they're used, whether they're licensed or not, and just kind of get a feel. All right, so that's probably about as much as I'm going to go through with at least with the RF spectrum perspective. So from that perspective, and maybe I'll pause for a second and see if there's any particular question on any of those. We'll move into kind of RF transmission scheme. I guess this we caught a hiccup on one of these slides here, but basically this is our transition into the RF transmission schemes. Any questions on anything to do with RF spectrum, what it is, why it's used, what these allocations are, who the FCC is, what those allocation maps meant, licensed versus unlicensed, anything like that? And if not, we'll move on to the RF transmission schemes.
Yep, no questions yet.
Okay, Very good then. All right, so we may just fly through this, which would be great. So a couple of things that I listed out here. RF transmission schemes, first off, can mean a lot of different things. And so any one of these things that I have listed here can be a whole day worth of a discussion, if not more, if you really wanted to get there. So I've listed out a few things. We're going to go through each one kind of one by one to kind of talk a little bit about what this is from an RF transmission scheme perspective, maybe what some of the pros and cons are to some of these different things. And I kind of did, you know, this versus that with two somewhat similar topics so that we can have a little bit of a discussion around two similar topics as we move down the list here, and hopefully give you a little bit of background on how that applies to an RF transmission scheme, what kind of spectrum attributes it has, how it's efficient, maybe not so efficient, things like that. So first off, Simplex Communication. If you see here, we were talking about Simplex versus Duplex. So we'll define these things initially here. So what do we mean by Simplex RF communication scheme? So Simplex means only one direction communication. So a single direction communication. So you'll see up at the top right, a transmitter is talking down to a receiver in the home, and this happens to be a representation of over-the-air broadcast TV. Another example might be AM/FM radios of Simplex communication, or a public address system, maybe at your school or university, what have you, when somebody at a principal's office or some headquarter office on the campus is making an address to the campus students. It's typically a one-way communication, a Simplex type of communication. Also, one-way AMR. AMR is automatic meter reading, I believe, is the acronym. So for some of you who may, I know my house within the last year or two, they've installed a smart meter on it. So as it's no longer a meter reader guy coming once a month, reading the meter and moving away. Now they drive a vehicle down the road and read these meters. Well, sometimes they do drive a vehicle, other times they're meshed, so they don't even need to drive a vehicle. But anyways, so basically it's a one-way communication of a meter of some sort. I'm using in this particular scenario a gas meter or electric meter on the house, feeding information to some kind of collector in one direction so that they can keep up with your billing for that month cycle and your usage, your power usage. Duplex RF communication, how does that differ from Simplex? So in this scenario, it's basically two-way communication. So at both ends of the path here, or the RF communication path here, we have a transmitter and a receiver, both at the home and at the tower location. So two-way communication, what we call sometimes uplink and downlink. Within this duplex RF communication, you can actually break it down even further and talk about, oftentimes you'll hear terms like half duplex or full duplex, and what does that mean? So half duplex is basically saying, although I have two-way communication, I can only communicate in one direction at a time. So for some moment in time, I'm talking in the downlink direction, and then pause, stop, full stop, and now I'm going to talk in the uplink direction. A great example, very, very common example of this that probably everybody who's listening is utilizing in some way, in some place, is Wi-Fi or wireless LAN. Wireless LAN is a half duplex communication device. So your laptop talking to the Wi-Fi router somewhere in your house, it's talking when your PC is talking to the access point, nobody else is talking, and the access point isn't talking to you. And then when your PC is done talking to the access point, and the access point needs to say you hit a URL to go to some web page, you type that in on your PC sends it to the access point, goes to the internet, and then the access point sends the information about that website back. It's a half duplex type of communication. Full duplex is another term you'd hear. So this is basically where you would be sending information in both directions simultaneously. Great example of that is cellular phones. 3G or LTE's type of technology, you'll probably see a little icon saying LTE or 3G on your Apple or on your Android or what have you when you're talking on a cellular network. And that's full duplex. When you're talking to your friend on a phone call, you're sometimes talking over top of each other, and that's because you're able to talk in full duplex type mode where both uplink and downlink is happening at the same time, and that's why sometimes you get talking over each other. Hopefully it doesn't happen too often, but that's a type of technology what allows that to make that happen.
So Dave, is it fair to say that a half duplex scenario is you only need like 2 radios, one at each end, to have a half duplex, but a full duplex, would you need 4 radios because one would always need to be receiving and one would always need to be transmitting at each location?
Not necessarily. It's a good question. It's a good question. I can see how that could potentially happen, but no. You don't necessarily need to have 4 radios. So licensed microwave, it's more about the what type of I'm trying to think of the term, what type of a duplex scenario is actually taking place, and we'll talk about it in the next coming up slide here. But there's things called time division duplex and things called frequency division duplex. Time division duplex is more of a half duplex type of operation. We'll see a pictorial about that. And frequency division duplex, which you see in a lot of licensed microwave solutions that are supporting cellular networks, and hence part of the reason why you can talk in these full duplex type scenarios. Frequency division duplex allows for you to be able to talk in full duplex, and it's still just 2 radios talking to each other. It's not 4 radios talking to each other that allows you to do full duplex. Hopefully maybe on the next slide here, or next couple slides, I can't remember exactly where it is, maybe pictorial will give a little bit of a visual of what I'm trying to convey here with 2 radios still being able to do full duplex type of communication. Does that answer your question, or is there more to that?
Yeah, no, that was it. Thank you.
All right. No, very good, very good. Oh, well, here we go. So right into it. So our next thing that we're going to be talking about, again, time division duplex. We're going to be talking about time division duplex versus frequency division duplex. So time division duplex uses 1 carrier frequency and then reverses many times. When I say reverse, it means in one scenario, if you look at just the top, let me see here if I can use this little mouse pointer thing here again. If you look at just the top section here, so in one moment in time, we are transmitting from the left-hand radio over to the right-hand radio's receiver. And then during that time, nothing is happening from the transmitter of the right-hand side over to the left-hand side. The transmitter on the left-hand side is fully consuming the channel or the carrier frequency during this moment in time. Then pause, full stop. The transmitter shuts off for a moment on the left-hand side, and now the transmitter on the right-hand side now has the time to send information from his radio over to the receiver at the other side. So that's called time division duplex. I'm chopping up time. So for some moment in time, one of the transmitters is talking to the receiver, and then pause, stop, then you reverse the direction. Transmitter at the other side is now transmitting to the receiver at the other side, and you're using that same carrier frequency. That's one of the niceties about time division duplex is it's somewhat frequency efficient. You only need 1 carrier frequency, but you have a little bit of latency, you have a little bit of time delay. You're talking in a half duplex fashion. Now this reversing scenario typically happens very quick, 200 times per second, so every 5 milliseconds this is switching back and forth, so it's very fast, pretty much negligible for voice communications or things of that nature with the latency. Hey Colin, are you still there?
Yep.
Yeah, okay. I just heard, I think maybe you muted or something like that, and I heard dead air, so I was concerned maybe I dropped or something like that.
No, no, we're okay.
Okay, all good. So let's move then to the next slide. I get this little funky delay every time I kick in the mouse highlighter with my page down. Oh, look at that animation. If Hensley was on the line, he would say you have too much time to put any animation on there. All right, so now moving on to frequency. Well, let's go ahead and use that animation here for a second. So that kind of walks through what I was saying. So for first moment in time, the top transmitter is talking to the receiver, and then pause. During the next moment in time, the bottom transmitter is talking to the receiver to the left.
So hey, Dave, in this scenario, is there ever any collisions? So are they like super in sync that they just don't collide with each other?
Great question, and that comes to play with a topic we're going to touch on yet another slide. You're a great lead-in for this switching of topics. This particular scenario of whether we're doing time division duplex or whether we're doing frequency division duplex doesn't necessarily dictate whether you're going to have collisions or not. It's more about the scheduler that's defined for the radio technology that we're talking about. And we'll touch on that in a section, if I remember what I called it, synchronized versus unsynchronized, or no, something else. It was scheduled versus unscheduled, or random access, or something like that. Maybe you can, since you have the slide deck as well, you can trouble through. But needless to say, in a couple of, hold that question, and in a couple of slides that we'll come up with, we'll talk a little bit more about scheduled protocols versus random access protocols. And with the beauty of scheduled protocols is everything is scheduled as far as who talks when, for how long, in what direction. And so you don't get these collisions that can cause retries, which then makes latency go up, as well as really impacts your ability to scale any type of a radio solution, meaning add hundreds if not thousands of users onto that radio solution and think you're going to have any kind of a meaningful type of communication with any of these devices if it's not scheduled. Whereas random access is just a kind of a free-for-all. You kind of wait, you listen. If you hear nobody talking, then you jump on the channel and hopefully you get it. That's very prevalent in Wi-Fi type of solutions. So your home routers, your home Wi-Fi routers uses this random access type of scenario. So anyway, we'll touch on that. Maybe I've spoken to it enough where when we do get to those slides, I won't have to spend too much time on it because it was really only a glance over, but at least address the whole scenario that you're bringing up as far as collisions. All right, so we touched on time division. Now we move to frequency division. So this is the use of two carrier frequencies. So remember here on time division duplex, we are simply using one carrier frequency, one piece of spectrum, and we're reversing it as far as who's talking and which direction. So it's very efficient with that carrier frequency usage. Here it's not so much efficient. We're having to use two different separate carrier frequencies. One's dedicated to the top transmitter to receiver, the other's dedicated to the bottom, or the, I guess we'll call it the bottom transmitter receiver, and they can talk simultaneously because they're on two different carrier frequencies. The beauty here is that you have low latency because I don't have to pause anywhere in the communication to now let another transmitter talk for a moment in time, and then I can talk after that transmitter is done talking. I don't have that latency, but it's a little bit more usage on spectrum. So if I'm in an area where I don't have a lot of problems with spectrum congestion and I have lots of spectrum to use, then utilizing FDD may make sense because I don't have to deal with any type of a latency in my network.
Oh, hey, quick question here. Can we still use the same antenna for two different frequencies? So in a frequency division duplex scenario, can you use the same antenna?
Pretty much, yes. When you're dealing with these frequency division duplex type of technologies, usually these frequencies are close enough to each other that a same antenna can be utilized. It's not like one transmitter is using 900 megahertz and the other transmitter is using 5 gig, where those type of antennas are dramatically different in design, and you couldn't design an antenna that could do that same those two different frequencies in the same thing. So usually these transmitters and receivers, these two different frequencies, are in the same band. There's slight amount of separation to kind of give it what's noted here as a guard band that separates these channels. And so therefore the same exact antenna can be utilized, an antenna that's tuned for 5 gigahertz, or an antenna that's tuned for 2.4 gigahertz, or an antenna in licensed microwave that's tuned for 38 gigahertz. I think that hopefully describes it well enough. All right, so we'll move on. Next thing in that list, I thought I reinserted that list every once in a while to kind of catch up on where we are in that list of things that we're going to talk about on these scheduled frequencies. But anyways, we'll move on. Single carrier versus multi-carrier, OFDM being kind of the main example of multi-carrier. What's the differences here? This can be somewhat of a complex topic, so I'm very, very lightly touching on it here. I'm in no way, shape, or form going to try to get anywhere deep into this, but single carrier example being QPSK and QAM, which I believe was discussed as what these terms mean, at least generally in some of the prior Cambium College presentations. That might have been Hensley or someone that spoke to that a little bit. It's a proven technology. It's been around for years and years. It's typically a time division system that can provide fast dynamic capacity allocations, ideal for statistical multiplexing bursty sources. So advantages with some kind of a single carrier type of technology. It's proven. It's very, very simple to deploy. One of the disadvantages of it, though, is that it's somewhat more susceptible to interference and multipath, whereas OFDM type technology, it's a multi-carrier modulation. It's basically taken these signals and divided a frequency selective channel, or divided up these signals into a frequency selective channel, into a number of narrowband flat fading channels. It's a lot of complex RF talk that basically means it can mitigate interference and multipath a lot better than a single carrier type of technology. Actually, I think I may have this these things reversed here a little bit. So the advantage is it can actually mitigate interference and multipath. The disadvantages is it's more complex and perhaps a little bit more costly when you compare it to a single carrier solution. So Colin, you get some points deducted from you from not quickly catching that these were reversed and telling me that.
Yeah, sorry.
Yeah, no, yeah, it'll be typically me to try and blame my own mistake off of somebody else.
Not a good guy.
Okay.
I take it back.
There you go. The truth is coming out. Yeah. Okay. So, anyways, moving on. So this is actually can be somewhat of an interesting topic. Again, another one of those type of topics that you could really spend hours on talking if you really wanted to get deep into RF technology schemes and things like that. But I'll try to summarize this in 60 seconds or less, or so, somewhere in that neighborhood. SISO versus MIMO. What in the world is that? So typically it's referenced as techniques that are used on the number of antennas that are used in a transmitter and receiver. So SISO meaning single input, single output. It's what you see in the top part of the figure that's off to the right. A single transmitter with its single antenna talking to a single receiver with its single antenna as well. Basically, so in the SISO system, only one antenna is used at the transmitter, one antenna is used at the receiver. It's more or less what I just kind of said earlier. In the MIMO case, multiple antennas are used. So what's being depicted to the right is something that would be called 2x2 MIMO, meaning 2 transmitters and 2 receivers that are being depicted in this scenario here. MIMO systems achieve better bit error rate compared to SISO counterpart at the same SNR. I believe Seth talked about what the importance of SNR is and how you kind of utilize that to determine your ability to achieve better modulation rates in the scenario of interference. So hopefully you understand that terminology from the prior Cambium College session. MIMO systems also deliver higher data rates due to transmission of multiple data symbols simultaneously using multiple antennas. This technique is called basically spatial multiplexing. So let's see if we can kind of maybe distill that down a little bit. So if we look at that picture, the bottom part of the figure over on the right-hand side, we see those two antennas for the transmitter, the TX, talking to the two antennas on the receiver. You also see below that a couple of things called related concepts, antenna polarization, MIMO A, MIMO B, single payload, dual payload. Those three things really, the antenna polarization part can relate to either of the two figures, whether it's SISO or the MIMO. The MIMO A and MIMO B specifically relate to that MIMO picture. So that picture can operate in a couple different scenarios. It can operate in what's called MIMO A, and in that scenario it's basically with those two transmitters sending the same information, perhaps coded slightly differently, perhaps delayed slightly differently, sent out on two different polarizations. What is polarization? So if you're familiar with Polaroid sunglasses, what do those do for you? When you put Polaroid sunglasses on, it blocks certain parts of the light so that your eyes don't get glared by the sun. In some similar fashion, that's what's happening when you polarize antennas in certain ways. So one of those antennas may be polarized in a vertical scenario, one may be polarized in a horizontal, and what that's ultimately doing is trying to block or provide some isolation between what's going on the other antenna so that one antenna doesn't get interfered by the other antenna that's using the same frequency. So back to this MIMO A, MIMO B stuff. So what can happen depending on the environment and interference and things like what Seth talked about in the prior Cambium College scenario, if I am able to talk with the two antennas to the other two receive antennas in a very clear path and no issues with interference like that, I could potentially operate in what's called MIMO B, which means I can send different information on the two transmitters and thereby doubling my capacity between those two radios that you see, the transmitter and the receiver. However, if I'm operating in a very, very harsh interference-ridden, multipath-ridden environment, I may not be able to operate in that MIMO B where I'm getting double the capacity. I may have to deal with a lot of error correction, and so therefore I would be ratcheting down, so to speak, and operating in MIMO A. What's the single payload? The same information is going over the same the two different antennas with the hopes that at the receiver side, one of the two antennas is going to receive one of the two transmitted signals correctly, and therefore it adds more robustness to that RF link. So these concepts of MIMO versus SISO, and then once you get into MIMO, there's MIMO A, MIMO B. We utilize antenna polarization to help with all of this isolation between the two or the multiple transmitters, whether it's two or more. All of that kind of ties together. Again, that can be a conversation, that it can be a several-hour type of class in and of itself. But I'm just trying to give you some general foundation on this. Moving down in that listing here is something called MU MIMO, Multi-User MIMO, and this is a scenario where you can create isolation between different, you almost create little mini subsectors within your coverage pattern of a single radio, such that you can talk to multiple users simultaneously at the same time in that same spectrum, in that same channel, and not interfere with any of the ones that are being talked to. It's a pretty intense technology. A lot of things go into making that come about, but that's kind of like basically a next generation step from MIMO B to now multi-user MIMO, MIMO A, MIMO B, and then into multi-user MIMO. It's a way of enhancing additional capacity out of a potential limited amount of spectrum that you are able to operate in, whether it's licensed or unlicensed. And then XPEC is something that you may hear a lot in licensed microwave technology, but basically it's again a capacity enhancement type of protocol or attribute. I believe it's referencing cross-polarization interference cancellation. It's a way of using a single carrier frequency and doubling the capacity by kind of almost doing a MIMO type of thing, using it twice, 2 transmitters, 2 receivers, and making sure that one of the transmitters, when it's talking, is able to be canceled out of the receiver, the opposing receiver at the other end. So basically you're transmitting 2 different sets of information, and the other receivers are able to cancel out the opposing transceiver or the unwanted transmitter's information because it knows what you were sending, and it's doing this XPEC magic under the hood.
So I guess I could have been mistaken, but I thought, or I was under the assumption that XPEC had to do something with like the polarization of the 2 radios.
Yeah, well, it does. It does. And so again, the acronym talks about cross-polarization interference cancellation. And yes, when you're doing this XPEC, typically you'll have one radio talking in a horizontal plane and another transmitter within the same radio, or sometimes I guess it would be different radios, talking in the vertical plane. And then you have some logic connections between the 2 radios so that they can communicate with each other, kind of know what each other is sending out, and so if they know what the other radio is sending out, they can know what not to listen for. And this is completely oversimplifying it.
Yeah.
But generally speaking, if the 2 radios know what each other are sending, then they know how to cancel out what that guy is sending, and therefore be able to distinguish only their wanted signal. That's what XPEC is ultimately doing.
That's pretty cool. You're gonna have to tell me more about that later in detail.
Oh, yeah. So Hensley's the man on that.
All right.
I only know the acronym. All right. So moving now on to we're getting close to the end of this here, I believe. I think. So now this gets into a little bit of what you were talking about, this collision scenario, and how do you avoid collisions and things of that nature. So that more often plays into what type of a schedule, what type of a protocol are you using to control the access media or the media access control. High level, what I put here is a couple different things. Some channel access policies, typical ones. So random access or contention based. This is what you find typically in your home Wi-Fi router, is a scenario where it's first come first serve. As my PC operates on the Wi-Fi access, it's listening for any type of a pause in the Wi-Fi protocol that its radio is tuned for, and when it hears a pause, it says, I'm probably able to talk out and make a request to pull down Google or pull down some web page or send an email or whatever it is I need to do. So I'm just randomly listening, and when I hear pause, I'm going to send up and hopefully I'm going to get a request to allow me to make my URL page request, and then the access point will send back down the URL content once it gets it. Random access, that's kind of what that's all about. Controlled access, kind of as the name implies, it's controlled, it's scheduled. Another term for controlled is a scheduled type of scenario. And this is where everything is much, much more controlled at the RF layer or the MAC address access control layer. And that adds a lot to do with the ability to scale your networks. That adds a lot to dealing with controlling collisions, with controlling interference, with allowing you to be able to synchronize a network if you need to. We won't necessarily, I think perhaps Seth talked a little bit about GPS synchronization in his session, if I recall, so I won't really get too much into that here. But this whole channel access control policy is what kind of drives at the protocol level how these attributes are controlled. So let's talk now, move over here to the right-hand side of the screen, impacting attributes, for whether you're doing a random access type of contention-based or contentious contention-based type of protocol or more of a scheduled type protocol. Latency of data transmission. So if you're getting a lot of collisions, if you're getting a lot of back off and try again type of scenarios with a random access, one of the attributes with random access is your latency can kind of go up a bit when you're dealing with that as you start to scale more and more users asking for media access. Scalability, we talked about that. If everything's scheduled and you're knowing exactly when, how people are allowed to make requests, if you're knowing exactly when you're sending information down to devices, how much is being sent down by devices, things that we call quality of service, who gets priority for things. All of that is something that comes more with a controlled access or a scheduled access technology than a random access technology. Complexity of configuration can somewhat be debatably a little bit more complex with a scheduled or controlled access solution because you have a few more parameters that you need to make sure you tweak versus a Wi-Fi router. Simply set the SSID and your password and away you go. It's basically 2, maybe 3 at the most things you need to set and you're off and running. So that's one of the potentially the pros for random access. But again, you get what you pay for, and if the use case fits, then it's great. Flexibility of traffic services offered, ability to provide good QoS. We talked about that a little bit. Standards-based versus proprietary. So Wi-Fi is a standards-based thing. You're going to probably, because so many different vendors make it, oftentimes a standards-based solution might be a little bit less expensive. But again, it's a scenario of you get what you pay for. If it works for your use, for your home use, which most Wi-Fi routers do, you only have 5 or 6 or 7 maybe people at a time in your household, depending on how big your household is, ever really using the Wi-Fi access point. So that's more than manageable by most today's Wi-Fi routers. So standard base is fine. But if you're trying to serve literally hundreds of thousands of users in a cellular network, or at a Starbucks, or some stadium, the Bears stadium, or whoever's football stadium or sports arena, standards-based versus proprietary, that might push you more toward a proprietary solution that is able to deal with scaling to large numbers in a very controlled and quality manner. And then price delta we just kind of talked about. Synchronization, a synchronized solution versus a non-synchronized solution. I think there's just a couple of slides, and again, I think Seth may have touched on this, but maybe this is a slightly different animation to kind of talk about. So the need for synchronization, interference due to non-synchronization. So if you have a scenario here where you have multiple access points or base stations or some type of radio technology that are utilizing very similar frequencies, and they're talking at different points of times and receiving in different points of time, and they're all co-located at itself, this is a scenario where you're going to definitely, as this pictorial shows, green being transmit times, yellow or orange or gold, whatever color you want to call that, being receive times, you see that they're staggered and they're overlapping on top of each other. And when they overlap on top of each other, they are basically causing interference to each other because they're co-located and they're very loud, screaming. Somebody's mouth is screaming very loudly into somebody's neighboring ear. That doesn't work in human terms. It doesn't work in radio terms, no matter how well you build the receivers. So how do we solve these solutions with certain radio techniques? Synchronization. And it could be GPS synchronization. It just needs to be a common synchronization source if you're talking about a single site. And what this example now tries to show is that when you synchronize these TDD thing, this, if you remember in our slides before, what is this, an FDD or a TDD? This is TDD, time division duplex. Some part of the time I'm doing, in the green portion of the time I'm transmitting, and in the orange point or gold portion of the time I'm receiving. And then I cycle again, transmit, receive, transmit, receive, transmit, receive. And when I synchronize those start and stop times, nobody is screaming when another person is trying to listen who is right next to me. So this type of RF transmission scheme scenario, a synchronized network versus an unsynchronized network is a very efficient and scalable type of network solution architecture as well. That is it. That is it as far as deep as I wanted to go in today. So we talked about RF spectrum, licensed, unlicensed, value propositions with licensed use cases, and we talked about various different transmission schemes. Any questions at all? If not, then I was a great presenter.
Yeah. Yep. So as of right now, there aren't any questions. So
Okay.
if there is anyone that does have any questions, definitely start typing those up now. And I'll use this time to plug our community page. By the way, this has been recorded. This webinar has been recorded, and it will be posted to a community page along with the collection of all the other Cambium colleges that we've done so far. Along with that, you can find various other webinars that we do on a weekly basis and have been doing for quite some time. Those are a little bit more product oriented, so it's not quite the same thing, but it definitely is knowledgeable there. So it looks like you still don't have any questions, so I guess
Okay.
you were a good presenter, Dave.
Yeah, and amazingly, I wasn't even looking at the clock, but apparently I'm generally speaking on time.
Right on time. So actually, we do have one person. He said, "Wait," so I think he's typing up a question. So we'll give him a little bit more time to finish that. So
Do you have a Jeopardy theme thing you can hum?
I should have had that pulled up. Here we go. In the synchronization using GPS, all of the APs should have a GPS receptor.
So that's actually a good question. So in this scenario here, all the APs, you can create that synchronization in many different ways. As long as all of the access points have the same sync source, they don't necessarily need to have all dedicated GPSs attached to them. Envision that as this picture, hang on a second, I'm going to get my fancy dancy little highlighter. So in this scenario here, if you look here, you see what's actually trying to be represented here is a single pole, tower, whatever. It could be a single building where these access points are all basically co-located next to each other. There could be just a single, we call this device here a cluster management module, and a single GPS connection on this cluster management module. I'll draw in a little GPS, and it's feeding a sync signal to the CMM, and that sync signal is being distributed just simply via the Ethernet cable up to these access points. So as you were kind of saying, one scenario is, yeah, you could have a dedicated GPS attached to every single one of these access points, and now you have, depending on how many access points, what do we have shown here, 6? You can have 6 individual GPSs. That's a little bit overkill. It's certainly valid, and people do that. But you could also use a centralized box, a cluster management module, in this particular technology example here, where you have a single GPS that is then providing a distributed sync source that is the same sync source going to all these access points and being able to do this synchronized start time on all these access points at this co-located site. Now, if we had multiple sites where we had another one, a few miles away or what have you, then you would want to have your dedicated GPS on this site here as well. So in this scenario, you would have 2 GPSs, one that was going to this cluster management module, one that was going to this cluster management module that is maybe several miles away, or maybe what have you, but it can still potentially hear this other site, so you want to synchronize these things. Does that answer the question, I hope? And I'm sure you love my my Googling or my doodling.
Yeah, I think so. And if, oh, yep, he just said yeah. So there have been a few more questions typed in response to GPS sync. as well. So another one is most of the co-location issue can be solved via GPS. So what happens if the device doesn't support GPS? And I think you kind of answered that with the CMM, right?
Right, right. There are external sync pulse providing devices that can provide that. The access point or the base station itself doesn't need to directly take in a GPS. Most synchronized solutions, if not all synchronized solutions, are built to take in some type of synchronized signal, whether either via their Ethernet port or some dedicated sync port. You can do that many different ways. If it's a synchronized solution, then it's meant to take some kind of synchronous signal, and so it will have probably one or two, at least one, if not multiple ways of providing that sync source to be able to provide redundancy for if you lose sync source from one place, it can quickly pick up a redundant sync source from another place.
Cool. So in a sync environment, is it possible to change the GPS source for some kind of NTP device that could provide a time source?
So let's not, good question. And a lot of people ask that type of a thing. So a timing sync source that we're talking about here for is basically a synchronized 1 PPS or 1 pulse per 1 pulse per second type of signal that is being fed to all these access points, and that 1 pulse per second signal is then able to be triggered to define when is the transmitter going to talk and when is the receiver going to be talked. It is not NTP. It is not network timing protocol where you're sending a protocol that's telling you what's the time of day, what's the date, things like that. That is nowhere near the type of precision that is needed to be able to synchronize radio duty cycles or transmission cycles. It's not a 1 pulse per second type of protocol. So please, when we say a synchronized timing synchronized signal, we don't mean NTP, which is network timing protocol. That is just simply something that is used to provide time of day to devices so they can pick up automatically time of day, and most people utilize that for a number of different things, but mostly for correlating their alarms and syslogs and things so that everybody has the same time of day. If you have some problems, you can correlate alarms and events and things like that across your network from a single time source. Does that answer the question, I hope?
Yeah. So if you want to, give some sort of acknowledgement there, and then we can move on. But one other question while we're waiting for that: does ePMP, does that product support CMM? Just for knowledge purposes.
Sure. Sure.
Easy.
Absolutely.
All right. Well, so as long as we answered the NTP question well enough, that's actually all the questions we have. So,
all right.
Yeah.
Well, then, if you're not going to linger any longer for any straggling questions, then thank you very much for the opportunity to talk.
Yeah. No. Thank you for stepping up and giving the presentation. So, and thank you everyone for joining. This is a pretty cool program to be a part of, and it wouldn't be possible without the audience. So with that being said, everyone have a nice night.
All right, thank you. Bye now.